Hi, I'm David Teedy, and I'm a technical advisor in non-destructive evaluation. I would like to present an introduction to non-destructive testing, or NDT. This will be a very brief, basic overview of NDT, including a couple slides for each of the 6 most common NDT methods, followed by a few selected applications. Let's start with the definition. NDT is the use of non-invasive techniques to determine the integrity of a material, component, or structure, or to quantitatively measure some characteristic of an object. That is, to inspect or measure without doing harm. From the physics point of view, all NDT methods use some form of energy to inspect or measure non-destructively. Thus, there are many possible methods, depending upon the feature of interest. The most common methods are visual, penetrant, magnetic particle, X-ray, ultrasonic, and eddy current. Most of these methods are inherently visual. Some of the uses of NDE methods include flaw detection, leak detection, dimensional measurements, structural characterization, estimation of physical properties, measurement of stress or strain, and material sorting. NDE methods can be applied throughout the entire life of a component, from product development, sorting of incoming materials, during manufacturing, including secondary processes such as heat treating, during assembly, and for in-service damage. We will now examine the 6 most common NDT methods in a little more detail. Visual inspection is the most basic and common inspection method. In fact, you might say it was the very first NDT method if you believe that God created the heavens and the earth and saw that it was good. Visual inspection can be aided using various optical systems such as borescopes and microscopes. Video inspection can be performed in many locations which are hazardous or difficult to access. Liquid penetrant inspection is basically an enhanced visual inspection using a liquid which becomes trapped inside surface breaking defects. Once the excess liquid is removed and a developer applied to draw out the trapped liquid, the presence of defects can be easily observed. This simple idea can get very complicated in a hurry. Magnetic particle inspection is very similar to liquid penetrant inspection, except that it works by magnetizing the part. Thus, only ferromagnetic materials, those capable of being magnetized, can be inspected by this method. In this case, finely milled and coated iron particles are attracted to the flux leakage at the locations where the magnet is broken by flaws. Most of us are familiar with radiography. Visible light is just a very small portion of the electromagnetic energy spectrum. X-rays are a much higher frequency or shorter wavelength and are capable of penetrating many solids. The radiation can be created by crashing high-energy electrons into a target or from a radioactive source. In film radiography, the part is placed between the radiation source and the film. Thicker or more dense regions of the part result in less exposure of the film. Here are some photographic and radiographic images of a few parts. Eddy current testing gets a little more sophisticated. All you need is for the material to be conductive. Here's how the physics works. An alternating voltage is applied across a coil. This creates an alternating current, which in turn creates an alternating magnetic field. When the changing magnetic field is placed near a conductive material, forces are exerted on the free electrons in the material, causing them to form eddy currents. These currents in turn create a magnetic field which opposes the applied magnetic field. Simple, isn't it? The end result is a change in the impedance of a circuit. Eddy current methods can detect cracks, measure conductivity, which is useful for microstructural changes, and measure coating thickness. Ultrasonic inspection uses high-frequency sound, typically from 500 kHz to 20 MHz, to find internal defects or characterize material. This slide depicts pulse echo inspection, in which a pulse of sound is generated by a contact transducer. The timing of the return echoes in combination with the velocity of sound can be used to measure thicknesses or locate and size internal defects. If you scan an ultrasonic probe and plot the amplitude of the echo versus the location of the probe, one can create images. It is possible to select the echo of interest. The image on the left was created using the echo from the front surface. The image on the right was created using the echo from the back surface. The back surface echo is still influenced by the front surface, as you can see. Let's review now some of the common applications for NDT. Many raw products, such as forgings and castings, are inspected by NDT methods. NDT is often applied following secondary processing. Monitoring heat treatment is especially important, as this process changes the material properties, and variations in the heat treatment process often happen. There are many things that can happen to a part in service. NDT methods can be used to detect cracks, corrosion, erosion, heat damage, and so on. Eddy current inspection is often used to check for corrosion in heat exchanger tubes. I have witnessed this inspection being performed in our own boilers at Cummins. I wonder if you have ever thought about wire rope inspection while riding in elevators or crossing suspension bridges. I have. It is possible to inspect these ropes using electromagnetic and even acoustic emission methods. Did you know that inspection of storage tanks is a big problem, especially for nuclear waste materials? Robotic, ultrasonic, and video inspection are routinely used. Aircraft, of course, are subject to a large amount of periodically scheduled NDT. I have worked in this industry and was involved in finding 10,000 soft rivets on the first DC-10, acoustic emission monitoring a 1 million pound proof test of the horizontal stabilizer strut on the DC-10, and have even performed eddy current crack detection on the wheels of the Cummins corporate jet. Did you know that some military cargo planes are mounted with acoustic emission sensors, which tell the pilot when the aircraft is good for only one more landing? Jet engines are routinely disassembled, inspected by penetrant, ultrasonic, and eddy current methods, and then reassembled. I have met and talked to the pilot of United Flight 232, which crashed in 1989. Pilots have a book of instructions to follow for every possible malfunction. The book did not cover this failure mode, however. The turbine wheel exploded and destroyed hydraulic and mechanical linkages to the control surfaces. The pilot figured out how to fly this plane using only the engine throttle controls. The pilots and co-pilots were the last to be discovered and rescued because no one thought anyone could be alive inside the nose, which broke off and was severely crushed. The turbine wheel broke because of a hard alpha particle, which was not detected by ultrasonic or eddy current inspection. It is impossible to make calibration artifacts that small. Today, they set up the inspection on the smallest standards they have, and then add 20 dB gain. The pressure vessels contain a large amount of stored energy. Many NDT methods are applied to pressure vessels, including ultrasound, radiography, and acoustic emission. A lot of money is spent every year inspecting both rails and the rolling stock for defects which could lead to derailment. Rail cars containing specialized ultrasonic inspection methods periodically inspect the tracks for fatigue cracks. There are over 500,000 bridges in the United States. Bridge performance decreases with time. Most bridges get a visual inspection about every 2 years, but some get detailed inspection. Did you know that many bridges contain known large-scale defects? Periodic ultrasonic and radiographic inspection are not adequate to determine if the defects are becoming more severe. It was for that reason that I developed acoustic emission methods to detect crack growth in bridges. Several bridges are now fitted with sensors. Have you ever seen a buried pipeline which has ruptured? I have, and the damage can be extensive. Pipelines are routinely inspected using devices called PIGs, which contain ultrasonic or electromagnetic sensors to detect damage. I also worked on increasing the distance between acoustic emission sensors up to 1,000 feet for use on buried pipelines. The Liberty Bell has been the subject of a couple special NDT inspections. Hal Dunnigan applied acoustic emission sensors to the Bell when it was first moved to Philadelphia to detect any damage during transit. More recently, on April 6, 2001, during a regular tour, a man suddenly began to attack the Liberty Bell with a hammer. A Park Service ranger had to tackle the man to end the assault. It was reported that there was minimal damage to the Bell, which weighs over 2,000 pounds. However, there was enough concern about damage for the National Park Service to call in experts from Boeing to perform a non-destructive evaluation. Just about every component on a Cummins diesel engine either is being or has been inspected at one time. The block and head castings can have problems with porosity, cracks, core shift, type of iron, and physical properties. Magnetic particle inspection is used for crack detection. Ultrasonic inspection is used for wall thickness measurements, detection of porosity, and determination of type of iron. Eddy current inspection is used to check hardness and to find chaplets too close to the ID of cylinders. X-ray CAT scans, or computed axial tomography, is used to check the interior dimensions of new castings and to reverse engineer other castings of interest. Other castings have been inspected as well. A flexible ultrasonic light borescope was used to perform fluorescent penetrant inspection inside exhaust manifolds for cracks. Radiographic inspection has been used for 100% inspection of aluminum compression brake castings. Radiographic inspection is performed to qualify new vendors for flywheel production. Connecting rods are inspected by magnetic particle inspection, and the residual stress is measured by X-ray diffraction methods. The bushings in connecting rods are inspected for contact between bushing and rod using ultrasonic immersion C-scan inspection. Aluminum pistons are inspected for D-bond between cast iron ring carrier and the aluminum. Inertia welds on valves, steel pistons, and turbocharger wheels have been inspected using ultrasound. Valves have also been inspected for cracks in the stellite facing using eddy current methods. Crankshafts and camshafts have been inspected by magnetic Barkhausen noise for residual stress problems due to grinder burn, and by ultrasound for cracks. There is an ultrasonic method to measure the case depth on crankshafts after heat treatment. Many bolts, nuts, and other heat-treated components have been checked for hardness or case depth using eddy current methods. Eddy current methods were used to check the select injectors for proper ion nitriding. Eddy current methods have been used to inspect wire prior to forming into springs. Magnetic particle inspection is performed on formed springs. Even ground ceramic parts are inspected by penetrant methods for cracks or chips. Electronic components have been checked by radiography for continuity of internal wires. Piston pins are checked for inclusions using ultrasound. I could go on and on about many other applications, but by now I think you get the idea.